Hi, everybody. Today we are going to talk about the parts and components of a linear accelerator. Just going to bring that up right now. Okay, here we go. So I'm just going to break it down for you. Okay, in the head of the linear accelerator, there's lots of components. Everything that's needed to make photons, X-rays, are there. We need, now in order to have X-ray production, 3 things are needed. We need a cathode. We need the production of electrons. We need a means of accelerating those electrons, and we need something to decelerate the electrons. So the cathode, or is a part of the X-ray tube where electrons are produced. And that's produced by a process called thermionic emission, which we'll get into in a little bit. By providing a voltage from the cathode to the anode, we can move those electrons towards the anode part of the X-ray tube. They will decelerate and hit the anode, which is a tungsten target, and by doing that, photons are produced. The majority of photons that are produced are bremsstrahlung. Now, mostly that's produced at the anode, 99% is heat. Okay, so I just wanted to tell you that the cathode is part of the X-ray tube. There's an accelerator guide that moves the electrons along. There's an anode, which is the tungsten target, and then the treatment head. That whole thing is called the treatment head. And in the treatment head is the primary collimation, the flattening filter or scattering foil, which we'll talk about, a bending magnet, ion chambers, and secondary collimation or MLCs. So that's all in the head of that, and the gantry there. Now in the stand, where the arrow is on the left, is a cooling system, a circulator, and a waveguide. So there's actually 2 waveguides that are in the linear accelerator. One waveguide just helps to keep everything flowing, I should say, in the right direction. And the other waveguide, which is really the most important waveguide that they talk about, is how the electrons flow from the cathode to the anode. So again, remember what we need to make X-rays. We need a source of electrons. We need a means of accelerating those electrons, and we need a means of decelerating those electrons. If any of those 3 things are not there, we cannot have X-ray production. So on the right is the cathode. So the cathode requires a high current. The current gets, there's a filament, actually a tungsten filament in the cathode, and that gets very hot by the high current. On the cathode side, when that filament gets hot, electrons are boiled off. And the process of boiling off electrons is called thermionic emission. So now we have electrons sitting there in a cloud, and how can we move them from the cathode side to the anode side? Well, the way to move them is to apply a voltage. So we apply a voltage, and the electrons will now move from the cathode to the anode. But unfortunately, electrons move in all different directions. So we need a means to keep the electrons focused. And what we use is called a focusing cup. And the focusing cup, just make sure it's, it just makes sure that the electrons are flowing in a stream towards the target. And then once they hit that rotating tungsten target, they will decelerate and photons are produced. And again, the one of the reasons why the anode is rotating is to dissipate heat. Because 99% of what is produced at the anode side is heat. So here I'm just showing, in addition to having a high current so that we can boil off electrons at the filament, we also need a high voltage to produce X-rays. And so we need a high current and a high voltage. So, we can't just plug in a linear accelerator and use the same type of voltage that we use for a toaster or a household appliance. We need something much, much stronger. So we have something in our room called a modulator cabinet. That modulator provides high voltage, direct current, actually, pulses, the magnetron and the klystron. So it provides the voltage for the magnetron and the klystron. Now you don't need both, you need one or the other. A magnetron with a G generates microwaves, and a klystron amplifies microwave power. So at the same time that we're generating microwaves, we also need those electrons to be produced. And like I said, the cathode is the negative side of the X-ray tube, and it consists of something called the electron gun. And that electron gun contains a filament. It's a tungsten filament that when it gets really hot, electrons are boiled off in a process called thermionic emission. And then when a voltage is applied, they will eventually go through a waveguide. So the waveguide is a hollow tube which transports the electrons to the anode. So it goes from cathode to anode. Okay, so now we see, you can see a suitcase up there. The anodes are now traveling towards the anode. And in the waveguide is also has the focusing cups, which ensure that the electrons are traveling in a straight path. Now, before the electrons reach the target, they go through a bending magnet. And what the bending magnet does is it laser focuses the electron stream to hit an area of the target that needs to be hit. So the anode, again, is the positive side of the X-ray tube. It's made of tungsten, which has a high melting point because a lot of heat is being generated, and it's rotating. And this whole process of this X-ray tube is done in a vacuum, meaning that there's no air or gas in it. It's in a vacuum. So this way, electrons are not interacting with any other particles. So it's at the anode where those electrons, when they slam into the tungsten, they're now being converted to photons. And as photons emerge from the anode, they're going in a variety of directions. So that's why we need something called a primary collimation, which only allows the forward traveling X-rays or photons to pass through, and it absorbs the scattered X-rays traveling in the lateral direction. And in addition, the maximum field collimation or field size that we can have on most linear accelerators today is 40 by 40. And so the primary collimation defines the size of the radiation beam. Okay, so now everything is going well, but what we need to do is before the photons hit the patient, we want to evenly distribute the photons across the beam. We want to harden the beam. So a flattening filter is a cone-shaped filter that absorbs more photons from the center of the beam than the sides to create a uniform photon dose measurement. So there's two things that basically do the same thing, but one is done with photons and one is done with electrons. So with photons, we have something called a flattening filter. And the flattening filter is basically going to make sure it's an even distribution of photons. If we didn't want to use photons and we wanted to treat with electrons, then we don't need those electrons that are traveling from the cathode to hit the anode. Because when they hit the anode, photons are being produced. So we don't need the target in the way. So the target would move out of the way if we just wanted electrons. But we would have something called a scattering foil that would, there's a carousel that can move either the flattening filter in or the scattering foil in. And we would just have the scattering foil that comes in, and that would make sure that the electrons are evenly distributed across the beam. So once the photons go through the flattening filter, or once the electrons go through the scattering foil, they go through the ion chamber, or they come in contact with an ion chamber, and that's used for dose measuring and beam quality monitoring. So we want the ion chambers make sure that the dose that's going to be delivered to the patient is measured and controlled. And that's why it's very important that we have 2 ion chambers. And the reason why we have 2 is because if the first one, it's basically a backup for the first ion chamber, if the first one fails. And the last thing, the X-ray beam is almost ready for the patient, but it's going to go through a secondary collimation. So we need to make sure that the shape of the X-ray beam matches the shape of the tumor. Sometimes in the past that was done with Sarabin blocks that you put into the head of the machine, but today we use multi-leaf collimations. And the MLCs are also made out of tungsten, and in a Varian machine, there's approximately 100, usually it's 120 leaves, and they can move independently to make, very complex shapes. Thank you, and I hope this was helpful.